So in section 2, we're going to talk about representing distributions with a graph. So basically different ways to visualize our data. So we've talked about discrete and continuous variables and qualitative and quantitative variables. Just to remind us that a qualitative variable places individuals into one of several categories, but they're non-numeric. So for example, one variable would be format, and notice that these radio station formats are non-numeric. That makes them qualitative. These over here is the number of stations in that format. The count is not a variable. Okay. Again, the vocabulary that I'm kind of going through is important. Okay, the count is not a variable. So we have here, if we're looking, we have a frequency table where you just have the raw numbers of how many. And then we have a relative frequency table where these are given as percentages. In a relative frequency table, your percentages should add up to 100% if you add all of them up. You may differ by like a small decimal point based on rounding. Everybody okay with this idea? So a frequency table like this, or relative frequency table, is informative, but maybe not that useful at quick glance. Like you have to really kind of look at it carefully and slowly to kind of see what's going on. Oftentimes, it's easier to represent the same information visually with something like a bar graph or a pie chart. So if I take my frequency table, I can convert that into a bar graph. And here it's very easy to see what are the like most popular formats and the least popular formats. It's visual, it's staring you right in the face. There's not a lot of comparison to do. And you can actually see get an idea of like how much more popular is like news radio than contemporary hits radio. So if I take my relative frequency table, I can convert that into a pie chart where again, pretty effective at displaying, like what are the most popular formats again, right? Stares you right in the face. You can glance at it quickly and go, oh, what's that big slice? Or what's that tall bar? What's that small bar? Very easy to see. Everybody's cool? Now, typically, if you have to choose, the bar graph is typically going to be a better choice than a pie chart just because your bar graph is more flexible. You could use it in a variety or a wider variety of situations. So you kind of have to have a relative frequency chart to make a pie chart where everything adds up to 100% kind of thing. But bar graph, you could use that whether you have frequency just counts or relative frequencies with percentages. It is doable for either. So let's talk about when we're drawing a chart or a graph, what are things that we need to kind of keep our eyes on. So when you're drawing we'll start with a bar graph. When we're drawing a bar graph, The bars should be equally wide, right? The width of the bars, so you don't want to like suggest that one category is like more valuable than the other. The width should be kind of uniform. You don't want to make like something, and then a little tiny skinny one, right? Like, and I don't know if this is probably less common because we don't read magazines much anymore, but I can tell you like a million times in my life I've been reading a magazine and they have a bar graph where it's like stacks of apples or something to make up the bars. Don't do that. Like it's exciting for a magazine, but it's like poor statistical practice. So again, the two things here to keep in mind: don't make the pictograph, the one where we're stacking up little apples or whatever, and be careful with your scales. So the widths of your bars should be uniform. The tick marks on your y-axis should be uniform. So another type of table, rather than just the frequency or relative frequency table that includes one variable, is a two-way table that involves two variables. So we have two qualitative variables, and we're organizing where the counts are organized into a row variable and column variable. So for example, we have this two-way table here, where we have our chance of getting rich as one variable, and then our gender as our second variable. So if I read this cell that says 96, that says in our data set there were 96 females that had almost no chance of getting rich. Everybody's cool with that? So if I look at this table, I can also read how many females were surveyed. So if I look at the female column, that's 2367. How many males were surveyed? 2459. How many total individuals were surveyed? 4826. Kind of see how I'm reading this? So like the 758 says there are 758 males with a good chance of getting rich. Does everybody feel okay on how we're reading this two-way table? It's not super complicated, but like it's really important that you're able to pull that kind of information from a two-way table. It'll become more important as we go on and do other statistics. Okay. So another situation that we might want to employ is using grouped data. So if I have a discrete data set, like number of children, in a household, that's discrete, right? Because you're only going to have whole numbers of children. We might want to group like families with no children with few children, like one or two, families with a medium amount of children, 3, 4, 5, families with lots of children, 6+. That might be something we'd want to do. Typically, to group data, you want to find your highest and lowest responses, and then arrange your data into larger groups of equal size ranges. So you don't necessarily want to make the quantities in the groups the same, but the range of the group should be the same. So if I have, say, one group that's range is 10 to 15, the next group should not be 15 to 30. You'd want like 15 to 20. You guys kind of see that? Because if we take groupings of unequal size, again, that can result in bias. And once we've made our groups, then we can just count the number of individuals to go into each group to make our new table. Is everybody okay with that? This is something you'll have to do when we do our IAs, is group data. So we'll, again, all these things that seem like the school, like this seems very simple, like what's the big deal? It's like you're gonna have to do this in practice. There's a lot of like do's and don'ts. It is very simple, but there's lots of stuff to remember. And when grouping, using percentages, i.e. relative frequency, can be useful, especially in situations where like the counts in your groups are very different. So an example here, Ryan records the number of tardies each of the 20 students in his class has over the course of the semester. Looks like this one must be Allie. That's probably Maya. Gotcha. So here's our raw data. If we want to group this now, maybe we'll group this from 0 to 2, 3 to 5, 6 to 8, 7 to 11, and total. What is the range for each group? Well, there's 3 possible responses that go in each group, right? 0 to 2 includes 0, 1, and 2 tardies. 3 to 5 would include 3, 4, and 5 tardies, etc. But the range is really 2, because the distance from the number 0 to 2 is 2. But there's 3 possible responses that go in there. So we made our groups. Notice each group has the same range. So now we go ahead and count. So 8 students had 0 to 2 tardies. So 1, 2, 3, 4, 5, 6, 7, 8, etc. The total still was 20 because we knew there's 20 total students to begin with. Everybody's cool with how we did that? What if I want to turn this into a relative frequency? I'm just going to take the 8 and divide it by 20. The 4 and divide it by 20, etc. So those are my relative frequencies. Notice they add up to 100%. That should always be the case in a relative frequency table. Or very near 100%. It could differ by a tenth or so if there's rounding involved. Everybody cool there? Was there any reason that we used to group our tardies this way? Not really. It was just, could have you done a range of 3 and gone 0 to 3 and then 4 to 6 and then 7 to 11 or 7 to whatever? Sure. Would have been okay. This is just what we did. If I want to group continuous data, so remember the difference between discrete data and continuous data. Discrete is like the variable can take on only whole numbered values like 1, 2, 3, 4, 5. Continuous can take on any decimal values. So there's always like infinitely many responses that could go into a continuous group. So grouping continuous data. Again, we start by finding the highest and lowest values in our frequency tables, arrange our data into groups of equal ranges. So one important thing is to decide on your method of boundary. So like, is it, say we're taking 10 to 15, does that mean your responses could be 10 less than or equal to x less than or equal to 15? Are the endpoints in the range? Are they not in the range? So that's what I mean by the boundaries. So typically your boundary would have one side is in and one side is out. Like you'd probably go 10 is less than or equal to x is less than 15. So things equal to 10 and up to but not including 15 would go in. But again, you want the same sized ranges for your groups, and then we count up our individuals. And again, relative frequencies can be helpful in some cases. All right. So if I set up my classes using continuous boundaries, so let's say we suppose we recorded the heights of plants that ranged from a smallest plant of 2.8 centimeters to the biggest plant of 28.6 centimeters. So I go 0 to 5. Notice that the first group does not include 0, but doesn't include 5. The next group includes 5, but not 10. And we kind of follow that same pattern throughout, right? Where the bottom of my range is included and then top of my range is not. Everybody's happy there? That's like one convention. This, I think, is the clearest of the conventions because it tells you exactly what's included in that group. It's unambiguous. Another convention would be to set our use discrete boundaries. So again, new example, suppose we recorded weights of players at a soccer game. We have described our boundaries this way. So I like this method less because what this first range or this first category is really describing are the players like 60.5 kilograms less than or equal to X, less than or equal to, or less than 65.5 kilograms. We've kind of written it as whole numbered, like a discrete boundary, but notice that there's like some implied rounding, because where would the 65.6 kilogram person go? It gets rounded up into the 66 pile, and the 65.4 kilogram person would get rounded down into the 65 pile. So again, you'll see this will happen in examples, homeworks, whatever. Not my favorite. I vastly prefer this kind of a setup where it's super duper clear exactly what's going in where. But you'll see this, and you can use this. I just don't like it as much for clarity's sake. Does that make sense? All right. So what is the difference in the two boundaries we've described here? Well, I notice this one includes 0, but doesn't include 5. This one doesn't include 0, but does include 5. We have to make sure we're paying very careful attention to those less than or equal to, those inequalities in our boundaries. They are quite important. So, is there any drawback to using this grouped data, right? Like, especially if you have continuous data, it's really difficult to like make a frequency table without grouping, because you could realistically have infinitely many possible responses, right? If you're measuring weights of people, you have 12 and 12.1 and 12.01 and 12.25. It's like, this is, yeah. Is there any issues where we are with making grouped data? Well, in a way, yes. Like you lose a little bit by making groups. So if I have all the individual data, I can find something like a mean for the entire data set. If I have just grouped data, I can't find the mean exactly for the data set anymore. I could approximate it. We'll talk about how to do that in the future. But that's the issue, is that we lose a little bit of information by using grouped data as opposed to like the raw individual data. So if I want to make a calculation and all I have is a grouped frequency table and I don't have any of the raw data, I have to make an approximation. To use that, or to make that approximation, I'm going to use something called a mid-interval value, which is just like the halfway point between the upper and lower boundary for the particular category or the particular group. So let's see an example here. So let's go back to this plants example. So here's our scenario. This is our grouped frequency table. We have no individual raw data for this. So I'm going to start by calculating the mid-interval value. So what is the halfway value between 0 and 5? $2.5, right? How did I get that? 0 plus 5 divided by 2. What's the halfway between 5 and 10? 7.5. 5 plus 10 divided by 2. And so on and so forth, right? Now, what this mid-interval value would allow me to do is I can approximate a mean for this data set by taking the mid-interval value, multiplying it by the frequency, and then doing that for each class or group, and then dividing by the total number of individuals. Everybody's okay with that idea? Oops, wrong way. Let's do another one. So here, what's going to be the mid-interval value for 61 to 65? So we have to be careful here because the lower boundary is what? It's not 61. This is continuous data because we're talking about weights. It's actually 60.5. And what's the upper boundary? 65.5. So if I take 65.5 and subtract 60.5 and then divide by 2, I get 63. So you have to be a little bit careful here in identifying that, we're talking about something that's continuous, even though it's written as a discrete range. And you see now why Mr. Kulik doesn't really like this kind of a setup, right? We're trying to trick you a little bit. Now, if you just kind of intuitively looked at this and went, well, halfway between 61 and 65 is 63, would have been okay. But like showing your work, a little bit different, right? Okay. So what can we do with this mid-interval value? I've hinted at this already. Oops. We can use that mid-interval value as an approximation, like an estimate for the value of every individual in that class. Now, it's not true, right? The individuals in that class certainly all don't have the same value, but it's a safe estimate to do a calculation with. And we've mentioned that now a little bit. Okay. Another way to represent data is with a histogram. Now this is important. Like, we like histograms, and they're different than a bar chart or bar graph or a pie chart that we've looked at already. It's like the most common way to or visual representation for distribution for one quantitative variable. So making a histogram, we're going to start by dividing our data so that we have classes of equal range, right? So the widths of our ranges are the same. We'll count the frequency, or maybe we want to calculate a percent, get a relative frequency for the individuals in each class. Will depend on the context or the question, which one you might want to do. To get the relative frequency, you need the frequency table to start with anyway, so it's, And then we're going to label and scale our axes. Really important. One of the most common mistakes on quizzes and tests that students make when they draw their graphs is they don't label their x and y axes. And we draw our histogram. Now, this is another key piece. Adjacent bars should touch. So the bars on a histogram are touching each other. There's no gap in between your bars, unless that gap is for a class that had no individuals in it. Is everybody okay with that idea? The bars on a histogram touch. I will mark you down if your histogram bars have any gaps in them that aren't supposed to be there. Just being very clear. Okay. So let's make a histogram here. So our frequency table, 0 to less than 5, 5 to less than 10, 10 to less than 15. All of our classes are here. Notice they all have equal width. And then the counts for each class are given here. So I'm going to start by making my histogram. I'm going to start by drawing my x and y axes, scaling them. That's putting tick marks and labeling the tick marks, and then labeling the axes. So my x-axis is the variable. So this table presents the percent of residents from each state who were born outside the United States. So that's what my x-axis is. And then the y is just going to be the number of states, because the count is just a count. Everybody's okay? Now I'm going to build this. So I scaled this. I noticed that my biggest count is 20, so I only need to go up to 20. My biggest range is 30, and each range is 5, has a width of 5, so going by 5s on the x-axis makes a lot of sense, up to 30. Is everybody okay with how I chose the scales? So my first bar is going to go from 0 to 5 all the way up to 20. My second bar is going to go from 5 to 10 up to 13, and so on. Notice the bars are all touching. Is everybody cool as to what a histogram looks like? A little bit different than a bar chart. Oftentimes a bar chart wouldn't have a range of values down here. It would just have like a label, right? Be like red, blue, green, or whatever, and they have the bar. Here, because we have grouped data, we use a histogram. All right, common mistakes. Watch out. Don't confuse a histogram and a bar chart or a bar graph. They are different. Don't use the counts or percentages as data. What do I mean by that? I don't know, but that's what you're trying to say there. So we use percentages or counts on the vertical axis. Okay. Okay, so, you're trying to compare two different studies that are both looking at the same thing. If study number 1 surveyed 50 people and survey number 2 surveyed 100 people, you're a doofus to look at comparing counts. You want a relative frequency, you want to look at the percentages. That's what item 3 is saying. And just because something looks nice doesn't mean it's actually meaningful. All right. Another way to represent data is with a dot plot. We saw an example of this in the previous PowerPoint, where we had the miles per gallons for the cars. So making a dot plot, we draw a horizontal axis, i.e. a number line, label it with the variable name, has to have a label. We scale it from the minimum to maximum values. Mark a dot above the location on the horizontal axis corresponding to each data value. So, for example, here is the number of goals scored per game by the 2012 U.S. women's soccer team. So if I look at my data the smallest one is 0, the biggest one is 14. So when I draw my horizontal axis, it's going to go from 0 to 14. And the label I put on it is number of goals scored. And then because I had just 1 0, I put 1 dot above 0. Because I had 1, 2, 3, 4 ones, I have 4 dots above the 1, and so on and so forth. Everybody happy there? Okay. Okay. So one of the things that we're looking for, or one of the purposes when we make a graph, is to try to figure out some information about the distribution in general. So if I want to examine my distribution, I'm going to use, I'm looking for overall patterns and departures from that pattern. So the things in general, what I'm looking for is SOCs. So the shape, the outliers, i.e. the departures, where the center of my data is and the spread of my data. So I'm looking for SOCS, SOCs. So if I ask you to describe a distribution, those are the 4 things that you should talk about. Is SOCs, shape, outlier, center, spread. We'll define what these things mean in a moment. Yeah, don't forget your SOCs. Okay. So let's talk about shape. When we talk about the shape of a distribution, we're talking about symmetry or skewness. So a distribution is symmetric if the left and right sides of the distribution are approximately mirror images of each other. A distribution is skewed to the right if the right side of the graph is much longer than the left side, and it's skewed to the left if the left side is longer than the right side. So if I look at this distribution, this looks symmetric to me, right? If I look at this side and this side, they kind of look the same-ish. Everybody's okay? If I look at this one, this is skewed right because it kind of tails off to the right. And what about this one? That's skewed left. Again, the center looks like it's about here. The left side is longer than the right side. That tails off to the left, skewed left. Are we doing any test, any calculation to do this? Just using our eyeballs. Everybody's happy? Okay. So if I want to compare two distributions, the things that I'm going to be comparing, shape, center, spread, and possible outliers. Again, the comparison will be using SOX. So we're comparing the household's size in two different countries, South Africa and the United Kingdom. So if I look at South Africa, if I want to find the center of this, I'm basically looking at where is like the middle data point. So if I count over here, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. And it's probably somewhere over in this like 4, or probably in this 5, 6 range. If I were to kind of eyeball things. Looks like there's probably about as much data over here as there is like over there. Oops. Nope. If I do the same thing here, the center of my data for the UK is probably in the 4, 5 range, right? Everybody buy that? So the center is pretty similar, 4, 5 or 5, 6. What shape would we give this? Anybody? Think that looks symmetric to me, right? It's basically all, the right side and the left side looks the same. What about this one, though? That's skewed right. You guys buy that? Again, we said the center was somewhere kind of over here. That right side is way longer than the left side. Outliers. Well, this 26-person household certainly looks like a possible outlier to me. That's pretty dang far from the middle of our data. And then the spread, again, if I look here, this looks like 3 to 26. So the spread is like 23 for this one. And this is maybe 3 to 6. So the spread is 3 on this one. Everybody's okay? So I'm just counting like the minimum to the maximum. What's the gap? So I just took the biggest value minus the smallest value. That's all I really did. The range is usually a good descriptor of spread, at least until we have a better calculation. Right? There's other calculations we can do, but we're not there yet. So I'm just kind of looking at the range. Another way to represent data is with something called a stem plot or stem and leaf plot. So the way we make a stem plot is I separate each observation into a stem. That's everything except the final digit, and then a leaf, which is the final digit. I write all possible stems from the smallest to largest in a vertical column, and then draw a vertical line to the right of that column. And then I write each leaf in a row to the right of its stem, and I arrange those leaves from in increasing order out from the stem, so from smallest to biggest. And then provide a key. Have to have a key. I will guarantee you on the quiz or the test, somebody's going to forget to put the key on their stem plot, and I'm going to mark it down there and be like, the key that explains what the stem and leaves represent. So here is our raw data. So if I look at the numbers, they're all 2-digit numbers. Everybody see that? So my stems are going to go from my smallest value, or my smallest first digit, which is 1, up to my biggest first digit, which is 5. So there's my stems. Notice I went down, like I'm increasing as I go down my down my plot. Now I'm going to write in my leaves. So for 1, I have 3, 3, 9, 3, and 5. But I'm going to write those in ascending order. So I'm going to have 3, 3, 3, 5, 9. Oh, so I put them in there and then I sorted them. Everybody's okay with kind of how I did that? Is this a finished stem plot? No, I don't have a key. So I'd write, for example, 4/9 represents in this case, these are female AP statistics students who has 49 pairs of shoes. Oh my God. 49 pairs that is a lot of shoes. I mean, girls, that seems like an absurd number of shoes. Is that an absurd number of shoes? I have like 5. And my wife is like, what is the matter with you?
I think I have like 7, 8.
I have like a work shoe, I have a dress shoe, I have a casual tennis shoe, and I have a running shoe. And like that's my life.
I like a walking shoe. Like I don't like a running.
Yeah. Anyway, that's me. I am not a stuff guy. All right. There's variations of stem plots. So one variation is to have a back-to-back stem plot. So if I have 2 different distributions that I want to compare, so say I have a male distribution and a female distribution, I'll do the same thing. I'll start, looks like my numbers have 1 or 2 digits. So I'm going to be looking at the first digit, but for the 1-digit numbers, that first digit really is 0. Like the 10 spot is my stem. So my stems will go 0 to 50 or 0 to 5. And I'm also going to do this as a split. I guess we're doing a split first and then a back-to-back. So the split means I'm going to go like 0 to 4 and then 5 to 9. Everybody's okay with how I'm doing that? So digits 0 to 4 go in the first stem and 5 to 9 go in the second stem. And then to split this, I'll draw a second bar and do the females on the other side. So notice I labeled the female side and the male side. And I'm not done yet because I need a key. So 4/9 represents a student who reported having 49 pairs of shoes. So I guess this was our AP students, females and males. Who's the dude with 38 pairs of shoes? Must be a sneakerhead or something.
I think the 35.
Yeah, that's a lot of shoes, man. Who's got a closet big enough for that? Not this guy. All right. Another thing that we might be interested in doing our distribution is talking about the percentile rank. So this definition is super important because it's easy to screw up. The pth percentile of the distribution is the value with p% of the observations less than it. You guys all took like the PSAT at one point, right? When they report your scores back, they give you a percentile rank, right? You ever heard of anybody getting 100%? Nope. You know why? You can't. It's impossible to have 100 percentile because you are a member and then there can't be 100% of the data below you because you are part of the data set. Okay? Could you be 0% rank?
No.
Yup. Because all of the rest of the data can be above you. You could literally be the bottom person and everybody's above you. That would put you at the 0th percentile. All right, so say this person, Jenny, scored an 86 on her test. How did she perform relative to her class? We could give her percentile rank. First thing I want to do is count how many people were in the class. So I'm just going to count the leaves on my stem plot here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 3, 25. So how many people were below Jenny? So I see Jenny and 3 people higher than her. So there's 21 people below Jenny. Everybody agree with that? So her percentile rank would be 21 out of 20, or sorry, yeah, 21 out of 25, or 84%. Is everybody okay with how I did that? So again, you're only counting the observations below. Another type of graph is a cumulative relative frequency graph. So this is like a build, like it's building up. The last data point is always going to be 100% because at the end of your distribution, you have 100% of your data accounted for. So let's look at an example. So this is the age of the presidents when they're inaugurated. I don't think this probably includes the last couple because these PowerPoints are pretty old. We made them a long time ago. Yeah, so I think that probably doesn't include Biden or Trump or maybe Obama? Yeah, I don't remember now. Might have included Obama. Anyways, you might be right on that. I'm terrible with what number present people are. Anyways, here's our frequency table. So 40 to 44, we had 2, 45 to 49, we had 7, et cetera, et cetera, et cetera. Yeah, I know it doesn't include Trump or Biden because they were 70 plus when they got elected, so there's not even a spot for them to go. Anyways, so here's the frequency. So our relative frequency is just the frequency divided by the 44, the total number of counts. Our cumulative relative frequency, we had 2, and then we have 2 plus 7, 9. Then we have 9 plus 13, 22. So we're just adding up the total counts above it, this selling up. The 22 is these 3, the 34 is those 4, etc. Is that okay? Now, if I calculate a cumulative relative frequency, I'm taking the percent. So 2 out of 44, that's still the same, but 9 out of 44, it's going to be different. In fact, it's going to be 4.5 plus 4.9, or I'm sorry, 15.9 plus 4.5 gave me the 20.5. There's some rounding going on there. If you're like, those two don't add up, it was rounding. Et cetera, et cetera. Notice the last category will always be 100% because it is including all of our observations. So if I graph my cumulative relative frequency, it's always going to be kind of like this S-looking curve. Is everybody okay with that? So again, little vocab breakdown. Cumulative means that we're adding up. Relative means it's a percentage. And frequency, it means we're talking about counts. Everybody's cool? And notice when we plot our points, the first plot is at the start of our range. So the dot is at 40, and the next dot's at 45. It's always at the start of our range. You guys see that? I know. I'm slide 27 out of 33.
No, that is not right.
Well, that's what I'm talking about. So again, this is going to be the if I want to talk about a cumulative frequency graph, it's going to be almost the same thing as the cumulative relative frequency graph, but instead of using percentages, we're using the raw count number. So if I go and I do the same cumulative frequency graph, so I had 2 presidents, and I had 9, et cetera, et cetera, et cetera, and I end at 44, right? What do you notice about the shape of these 2 graphs? They're the same, right? They should look the same. They may be like distorted a little bit from the, like the scaling, but if you like adjust the scale so that they looked, it'd be the same picture. Okay. So remember when we talked about SOX earlier, the C for center, there's kind of 2 measures of center. So the most common one that we'd be using right now is the median. That's the midpoint in the distribution. So you just count values from each end until you get to the middle. So we range all our observations from smallest to largest. If the number of observation is odd, that means there's going to be 2 values in the middle. Oh, no, if the number of observations is odd, it's just going to be 1 value left in the middle. But if it was even, there's going to be 2 middle values, and you just take the average of those 2. So this is commute times for New York workers. So to find the median here, we'll rank them from smallest to largest, and then just find the middle value. So when I did that, I got 20 and 25. Notice there was an even number of workers, so I knew that I was going to get 2. So 20 and 25 are the middle 2 values. If you look at that, it's going to be values like 10 and 11 or whatever. So to find the median, then I took the average of those 2 and got 22.5 as my median. Everybody cool on that? NBD? So the center alone can be a little bit misleading. Another useful description of a distribution should also include a spread. So finding the quartiles will be one way of representing that. The quartiles are like the 25th percentile, the 50th percentile, the 75th percentile, and the non-100th percentile. So again, we arrange our observations in increasing order, locate our median. The first quartile is the median of the observations located left of the median, not including the median. Okay. The third quartile is the median of the observations located to the right of the median, not including the median. And then we say that Q0 is the 0th percentile, Q1 is the 25th, Q2 is the 50th, Q3 is the 75th, and Q4 is the 100th percent. So if I have a cumulative relative frequency graph and I want to find my quartiles, well, the 0th percentile is 40. The 25th percentile maybe is like there. So I track that over and I track it down as maybe 51 or something. The 50th percentile I track over and down, that looks like 55-ish, et cetera, et cetera. So I'm just kind of making some estimates there. Is everybody okay with how I did that? So if I asked what is the percentile rank of a 60-year-old or a 65-year-old, I take 65, trace it up, and then trace it over and maybe say like 95 or something. Everybody okay with that? So you can go both ways. I can use the percentile rank to get the age, or I can take an age and get a percentile rank out of it. So this cumulative relative frequency graph is super helpful if you're looking for percentiles. You can read it right off the graph. You just have to go look carefully, I guess. So given that so the next here, what if we have a cumulative frequency graph instead of a relative frequency graph? So if there's 44 people, obviously the minimum is 0. And if I take this and divide this by 4, that first quartile is 11. So if I look at 11, and then I trace over and down, maybe that's 51 or so. The half of the people would be 22. So if I find 22 and I trace that over and down, that's 55-ish, etc. And notice that I'm getting the same values here that I would have with the relative frequency graph. The difference was I had an extra step here where I had to figure out like how many people should be in the quartiles in order to predict the age, right? So I had to figure out how many people should be in the quartiles before I could like draw that over and down to estimate the ages. For the cumulative relative frequency graph, I already have percentiles over here, so I don't have to do any conversion. All right, we're done with that. The homework is 1 through 12. But let's do some of these in-class examples here with our last 10 or 15 minutes. So try to wake up here a little bit. And I'll get out my random student generator to call on people if I need to, or you can just try to participate to the best of your abilities. Don't act like you don't know this. I've shown you guys this before, haven't I?
The code you made?
Yeah, the code I made.
I remember one time I made him make a pumpkin.
You've never seen it?
No, gosh, I made him make a pumpkin.
I've never seen
All right. Below are the percentages of 12 to 17-year-olds who post various types of personal information to their social media accounts according to a survey. So here's the types of personal information, and that's the number or the percent of the respondents who said they do that. Make a well-labeled bar graph to display the data. What would the scale on the x-axis contain? Nope. That would be the label, be the percentages of 12 to 17-year-olds. Yes, these guys would be the labels on our x-axis. And what would the y-axis be? Percent who post would be the label. And then the scales would go from, well, about 0 to 100, probably, because these are percentages. But, yep. And then we just build our bars, right? Everybody's happy? Okay. Would it be appropriate to make a pie chart for this data? Why or why not?
No.
Why not? Yeah, and in fact, the individual that posts photos of themselves likely might also be sharing the school name and the city or town where they live, and so you have a lot of overlapping data. But yeah, because this is not like it's just not an appropriate thing to make a pie chart out of. That was good enough. All right. In 2020 or the 2008-9 regular season, basketball player Dwayne Wade averaged 7.5 assists per game and 2.2 steals per game. The following pictograph displays this information. What's wrong with this and how could we improve it? What?
Oh, it's in the
Yeah. What's wrong with the graph? Great. Why do you think it's confusing?
basketball. I don't know, there's a lot of
I
kids.
think the lines are just like Yeah,
Oh,
that's
sure.
your eyeball like that one day this one.
You're using those stupid basketballs, right? Why not just use a bar? That would be an improvement. Absolutely. What's up?
They're different widths.
Yeah, right? The basketballs are different widths. It looks like this assist is gigantic and this steals is tiny when it's really, they're not that different. So, good. Example 3, we have 2 bar graphs here that represent 2 different jobs and their earning potentials in US dollars per week. Please note the same information is used to display both graphs. What is so it's the same information, you have 2 different graphs. What's misleading about using graph 2 instead of graph 1?
Where you start the numbers, the money per week.
Sounds accurate.
Yeah, one starts at 0, one starts at 800.
Mm-hmm. And if I look at this, what would you say?
They're made 800 more.
Yeah, that like this job is
Yeah.
gigantically bigger than this job. In this one, they're quite a bit more similar, right? And you nailed the issue is that you started at 800 here instead of 0. So that's good. Right? In this graph, job B appears to earn twice as much as job A. Over here, it looks like it's 5 times as much. You guys see that? Yeah, that's the issue. All right. Ooh, this is a fun one. All right. We need to complete this 2-way table. It's like a Sudoku.
We do that.
So I would start with this one right here. 4, because 4 plus 11 plus 3 has to give us 18. And then maybe I do this one here. About 85. Well, I mean, 350 minus 247 is 103, and 103 minus 18 should be 85. Right? And then so on and so forth. You just kind of keep going, right?
I was trying to add numbers.
Yeah, don't do that. All right, let me move. All right. So I'm going to put this answer up so you can see the table there. Sometimes I am just like so frustrated with go away. Okay. So how many students total have Androids? 85. What percent of students are seniors that use iPhones? 91 out of 350. So seniors and iPhones together. Everybody's okay? What percent of juniors use other phones? Not 11. Well, notice the question is, the previous one was what percentage of students. This says what percentage of juniors. Yeah, 11 out of 114. So you're looking at all of the juniors as your divisor as opposed to all students. Is everybody cool? Okay. Those kind of questions, super common. And we'll see it again when we do probabilities. I know, I'm excited too. I love probabilities. All right. So we want to start by making a frequency chart grouping with groups containing 5 scores. So for example, like 75 to 79. So what's our smallest score on our table? I see a 68 here.
68.
I think that's the smallest one, right?
Wow.
So I would go maybe 65 to 69 as my first grouping, and then like 70 to 74, and on. Okay. If I want to make and then I do my counts, right? If I want to make a bar graph, how should I label that bar graph? What should be the x-axis label? Great, percentage scored on IB math class or something? Yeah, fine, sure, perfect. How about the labels on our scale, on our x-axis? Yeah, great, the ranges, perfect. And then that y-axis should be, you can just call it count, to be honest with you, or number of individuals, or what, like anything like that is fine.
So is each box like a student?
Yes.
Okay.
So there are, whatever, 32 students or something here, 24 students. Now, how do I convert my frequency chart we would have made in part A into a relative frequency chart? So for each class, like 75 to 79, I take its count and divide it by the total number of observations. So again, for like that 65 to 69, there's just 1 in there. So I'd have like 1 divided by 24 or something. Is everybody okay with that? Okay. And then if I wanted to do my well-labeled bar graph, what's the only thing that's going to change from the first bar graph to the second bar graph in terms of the labeling? The y-axis label is not going to be count anymore. It's going to be relative frequency or percent or something, and it would go from 0 to 100, right? Everybody's okay? Will they look pretty similar, the two graphs? You betcha. You betcha. All right. So we're going to make another frequency chart. This time we're going to use these kind of specific ranges. So if I look at this, what's the smallest observation here?
11.6.
I see 11.15. Got you again. That appears to be the smallest. So like 11 to 12 could be our first. And then we'll go 12 to 13 and 13 to 14, etc. When we're writing those boundaries, we got to make sure the format stays the same, though, where the beginning of our bound has the or equal to and the end has the strict less than. Okay, so we do that. We'd count up. So like in the 11 to 12 range, I'd have 1, 2, Well, not 12 because it's a not equal to, but this one would be 3. So I'd have 3 things in that first category, right? Everybody's cool with how I'm doing that? And then if I wanted to convert that to relative frequency, I count this up, I see 24 observations, so the first category, 11 to 12, would be 3 out of 24. So that just turns into a percentage or whatever. Everybody's okay doing that? Okay. And then it says use your relative frequency chart to draw a well-labeled bar graph of your distribution of 100-meter times. We've done this now a couple of times, right? I want to point out to you that you can use Excel to do this if you're doing like homework problems and it's irritating to draw these graphs all the time, that you're more than welcome to like put the data into Excel and make a bar graph in Excel. It's actually probably pretty good practice because we'll use Excel again at other points in this class. So you can just copy those things in. I'm just going to make like some made up stuff here. Actually, I'm going to say like, so these would be like your categories. And you just highlight these. And then you do insert. And then we pick a chart. So I want just like the boringest bar graph I can get. And there we go, right? I just can change my labels and stuff in there, but I got like a pretty bar graph. Everybody's okay with that? And you can drop those into OneNote or whatever. If you're doing everything else on a sheet of paper, you just like, on the side or something and just, drop them into OneNote as you make them and like label them like 13.B or something. I don't know what you're doing. That's if you want to. I know that maybe that's a hassle more than just drawing it, but this is a good one. So if I want the average test grade here, how do I do that? If I wanted the average test grade for this data, the number of things, right? I think there's 24 of them again. Okay, what if I give you instead this chart and ask you to calculate the average? So you want to start by calculating the mid-interval value. So like 67, 72, 77, 82, etc. Okay, and then I'll do like 67 times 1 plus 72 times 1 plus 77 times 3 all the way out, and then divide that whole thing by 24. So you're doing like a weighted average, right? Like the 82 gets used 4 times. You could also write 82 plus 82 plus 82 plus 80, do it 4 times. You could do that too. Remind me next time and we'll do like some calculator stuff and show you like, can my calculator just do a lot of this stuff for me? And I will say, oh heavens, yes. All right, so I think we're just about out of time. We'll stop here. Remind me that we have to pick up and do some more of these in-class examples and show you some calculator stuff. I think with more time, I'll get the calculator out next time and really kind of unleash some of the power of our graphing calculator. It'll be exciting.